Hey, so what's up? So this video will try to solve binary tree level order traversal problem. So the problem is like super simple. We will be given a binary tree as input, and our job is to return all these nodes on level by level basis. So what do I mean by level basis? So the first level is basically the root node itself, 3. And the next level is node left of 3 and right of 3. So which is 9 and 20 because it's left and right of 3. And the next level is obviously nodes left of 9 right of 9, nodes left of 20 right of 20. So 9 has no left and right nodes, and 20 has nodes 15 and 7. So now if you want to classify all these nodes on level by level, 3 is basically the first level, 9 and 20 is the second level, and 15 and 7 is the third level. So the most important concept which goes behind solving this problem is to know what traversal algorithm to use. The reason is we are traversing level by level. So what traversing algorithm generally travels one layer at a time? It's obviously breadth first search algorithm. And hear me out. DFS, depth first can also be used to traverse the problem, but BFS is the best way you can use to traverse the problem. So if you want to check out how BFS can be implemented here, you can check out my friend's Robin's video, which will be on top. So now let's try to actually code this problem in Python. So to implement any BFS kind of logic, the first step is to obviously initialize a queue data structure. So I'm going to initialize a list and I'm going to call it queue itself. And we need another list to keep track of the current level. So for that, I'm going to use a list cur and I'm going to initialize it with the root node, because obviously for every level, the first level is obviously just the root node itself. So for any tree you take, the first level is just the root node. And to make it easier, I'm going to initialize with the root node. And what we're going to do now is we're going to traverse each level at a time. And we're going to append the left nodes and the right nodes to the new list and add it back to the queue itself. That's the whole concept. So before we understand what goes into the while loop, we will try to implement the other logic. So the first step is to obviously add the current level to the queue itself. And now we can empty the current level. So for the next nodes to take its place. Now the next level, as we saw before, is nodes left and right of the current level nodes. So we can just traverse through the current level. So the current level which we just added to the queue, so it will be present on the end of the queue, so which can be accessed using queue of -1, because queue of -1 also refers to the last element or the last list inside the queue itself. So for each node in the recently added level, if the node has a left element, we can add the left element to the queue. Sorry, to the current list. And the same concept goes for also the right nodes. So I'm just going to copy this. If the node has any right element, we can add the right element to the current list. Now we need to understand what goes into the while loop, because it's super important. When do we break out of the loop? So when do we break out of the loop? One thing you notice here is each level has at least one node. The first level has one node, the second level has 2 nodes, the third level has 2 nodes again, but the level after the third last level has 0 number of nodes. So if the current level has 0 number of nodes, which means we have reached the last level already and we can break out of the loop. So we can just call this while loop as while cur. So what this does is, if the current level is empty, so it's basically if it's an empty list, we break out of the loop. And so now we have added all the nodes level by level basis into the queue itself. Now, one thing we notice here is we are not adding the node's value, we're just adding the node itself, we're just adding node.left itself. So in order to add a node value, as we can see the class initialization here, dot val refers to the value of the node. So we can just loop through our queue and we can replace all the nodes with node.val. So we can actually add all the vals to a new list, vals list, and we can traverse now. For current node in current level in queue, and for node in the current level, what we are basically doing here is adding node.val to the vals list. That's what we're doing here. And we can just return the vals list. Now, before actually running this code, we need to make sure that we have actually solved all edge cases. So if I run this code, it'll probably run now. And I made an error. So let's see what's the error. While node dot left or none attribute. Yeah. So we made a mistake here. We don't have any left attribute to the node. So why is that? You can check what's our input. Our input is an empty list. So obviously, if our node has no root node, it means it doesn't have left and right nodes to it. So to solve this, we can just add one if condition before the while loop. If our input is empty list, so if not root. So basically the root is empty. If not root makes it if the root is empty, we return an empty list of items. That's pretty much it. I can run it. Yeah, I can see the code runs and it's actually quite fast. The last time I ran this code, it was actually faster than 95%, I assume. Yeah, but that's Leetcode. This happens. So the time complexity for this code is obviously O of n complexity because we are appending through each nodes and in each level just once. And the space complexity is also O of n because we're just having 2 extra lists to do this problem, and it's the size of the list is relative to the number of nodes in the tree. So the space and time complexity is O of n. So yeah, now let's try to solve a different variation of the same problem known as level order traversal 2. Well, now here you ask what's the difference between level order traversal 1 and level order traversal 2. So if you see the question for level order traversal 2, we are basically traversing level by level basis. 3 is one level, 920 is another level, 15, 7 another level, except we are returning in a bottom-up level order approach. So in bottom-up level order approach, 15, 7 is basically the 0th index, 920 is the first index, and 3 is the second index. So that's literally the same concept which we saw in level order traversal 1. We are traversing level by level, except we're returning the list in a reverse order. So one thing we can do is I can copy paste the same code which we did here, level order traversal 1, and I can just return it in a reverse order using this Python traversal method. This basically returns the list in reverse order, and I can run this code. As you can see, this program runs exactly super fast, 95%. And another thing which you can actually do here is instead of appending the current level instead of appending current level to the right of the list, which what append operation does, you can append the current level to the left of the list. So how do you append a list to a left of another list? Using insert operation in Python. Insert 0, cur. It appends front of the list. And here we are traversing through a recently added level, which is q of -1. But since we are appending in front of the list, the recently added list is basically q of 0 in this case. So, and literally pretty much the same thing, and we don't need to reverse here because we are just changing it directly, and we can run this code. Yeah, the program runs, and this is also 95%. It's super fast. And same thing what we did in level order traversal 1. This is time complexity is also O of n here, and the space complexity is also O of n. And yeah, it's super easy. So one thing I want you guys to try is to implement the same logic using depth first search using recursion. So if you're using DFS, you basically use a hash map kind of data structure. So it's very interesting. Give it a go.